So next up, we want to wire all these independent planks to one. And because in this specific scenario, we want the bridge to be able to torsion and flex as well as react to the mass of the creature, we want a constraint that will actually allow us to give us that degree of flexibility. So in this case, a spring is probably ideal because it can actually stretch and return to its rest position and give that kind of rope-like effect to the bridge. And because we want the actual left and right side of the plank to react independently in the y-axis, it's a good idea to use two sets of springs, one down the left and one down the right side. And that should be able to give us the actual quality we're looking for. So it's pretty easy to add all the springs. We'll just use the multi-constraint tool. And I'll quickly select all my control objects down one side. And then we can do the same thing down the other side. And just end that. So if we play that back, we can just take a look at what kind of effect we're getting. So the planks are actually strung together now, and they hold together pretty well. Obviously, there's some problems. The spring is clearly not tense enough to keep the bridge entirely together, but that's pretty easy to fix. So what we can do is just, with all the springs selected, hit Enter to edit all the springs' properties. So the one thing to remember about the springs is it's basically based upon Hooke's law, which basically defines how springs react. And more or less it states that a spring that is stretched twice as far will exert a force twice as great. So basically there's a linear relationship between the spring's length and the actual force it can exert. And that's basically known as Hooke's law. So if we actually look at the equation for Hooke's law, what we can see here is the force is equal to the spring constant times the difference in the spring length minus its rest length, so the delta in length, and subtract the velocity times the dampening constant. So these three constants are defined in the actual spring parameter operator. So for the spring, you've got the Kp, dampening Kd, and the rest length R. So you don't really need to keep in mind the formula all the time, but it's a good idea just to have that relationship in mind, that there's a linear relationship between the force it can exert and its actual length, and that kind of helps you in getting predictable behavior. So right off the bat, I'm going to increase the spring constant, so in effect increase the number of coils in the springs to make it a lot tenser. So if we play that back, you can see the actual bridge is holding together a lot better. Our little guy still falls off, and that's clearly because though we have these constraints gluing all the planks together, each board is still able to rotate independently on its own axis. So that means that they can rotate and spin, and the creature can fall through. So what we need is a third row of constraints to bind them all together, basically across their width. So what we want in this case, we could go with a simple hinge, and that would allow the planks to kind of rotate on one axis. But because we might apply forces and wind, we want a few more degrees of freedom for the actual boards to move. So for this case, I would suggest a ball and socket joint is ideal. And we don't want to apply ball and socket joint in between every plank, because if we do that, they're all stuck at a fixed length to one another. And we want the bridge to be able to actually sag a bit to gravity and stretch out. So what I'm going to do is avoid putting the ball and socket joint between both the first planks and the last plank. So we'll leave a gap there, and that allow the springs to take effect only there, and allow the bridge to sag, and then the ones in between we can actually lock together. So might as well just go and do it. It's not that complicated. Use the multi-constraint tool and apply ball and socket joint to all the middle planks. Once we've got that, you can see the default position of the ball and socket joint is at this kind of 90-degree angle. What we want to do is reposition that slightly so they're just in the center of the planks, and we've got all the freedom of movement we want there. You can see you can rotate in that position quite freely. So I'll set the initial state for that. And then if we play that back, now we've got a much better behavior with the actual planks. What I'm going to do is just go into the dynamics operator and turn off the collision detection to just speed things up a little bit. And we'll get more into actually tuning the collisions and how to optimally work with that in a little bit. So we'll play that back and just see how far our guy gets along. So you can see the bridge is quite bouncy, and we can improve that by increasing the dampening factor. So it's a little more absorbent, and it doesn't have as much of an elastic quality to it. But it actually works quite well, and it seems like our little guy is going to actually get right across, which is impressive. So you can see his footsteps are actually triggering oscillation in the bridge, and those forces, because there's no dampening, are being amplified, and you're getting a lot of shake. So we can minimize that quite a bit by going to the springs and tuning them. And a lot of the rigid body stuff is like that. I mean, you have to start with simple constraints and approximate the system you want, and you can see where it's starting to break apart, and you can apply other constraints and forces to kind of minimize those kind of effects, because rigid bodies naturally progresses if you don't have a lot of resistance and different forces keeping it constrained. It can kind of quickly blow out of proportion. So I can increase the dampening there and apply that to my springs. So right away you can see it's a little bit better. It's not swaying quite as much as before. So that's working quite well. In this case, I can also take my robot character, and it's quite easy to just duplicate that. So we can just do Control D and then rotate that around the center of gravity. Oh, sorry, I guess I want to rotate that around the view. So we can rotate that approximately 180 degrees, so it's facing the other way. And we're just going to translate that guy over here and then set the initial state for that guy. So we essentially just duplicated the rig and moved it to a new position and set the initial state, and that will allow us to actually have that react from that direction. So we can have this kind of showdown on the bridge between our two characters. And obviously this is a great thing about rigid bodies. We're not having to keyframe everything, so we can just run the simulation, see what happens with our characters, and tune it a bit more and get a different result.